Some stars die quietly, others leave behind something so extreme that it can bend light, crack its own surface, and tear matter apart atom by atom. Tonight, we're stepping into the astonishing science of magnetars, the most magnetic objects known in the universe. If you enjoy calm, immersive science documentaries like this one, please take a moment to like the video, subscribe to the channel, and share it with someone who loves space and cosmic mysteries. And thank you, as always, for being here. Before we begin, I'd love to know what time is it where you are, and where in the world are you listening from? Please let me know in the comments. And now, let's begin. A magnetar begins long before magnetism becomes the story. It begins inside a star so massive that balance itself is only temporary. A star held together for millions of years by a quiet contest between gravity pulling inward and nuclear fusion pressing outward from the core. In that central furnace, hydrogen nuclei are forced together under enormous heat and pressure, forming helium and releasing energy in the process. That outward energy is what keeps the star from collapsing under its own weight. For most of its life, the star exists in that state of dynamic equilibrium, not at rest, but in a continuous negotiation between compression and release. From a distance, such a star may seem steady, even calm, but its stability is not permanent in the way a mountain or a planet may appear permanent. It is a temporary structure built from fuel, and like every fire, however grand, it lasts only as long as something remains to burn. What matters here is that a magnetar does not emerge from an ordinary stellar ending. It comes from a star already living close to the edge of physical extremes, a star with enough mass that when its internal economy fails, the collapse that follows is not gentle, not gradual, and not reversible. As hydrogen in the core is depleted, the star begins to change from the inside out. The first stage of fusion does not simply stop and leave the star empty. Instead, the internal structure reorganizes. The core, now richer in helium, contracts under gravity, and that contraction raises the temperature further. Around it, hydrogen can continue fusing in a shell, while the outer layers of the star swell outward. This is one of the most important features of massive stellar evolution. Death does not arrive as a single event, but as a sequence of increasingly compressed solutions to the same problem. Each new stage buys time, but each stage also shortens the future. When temperatures climb high enough, helium begins to fuse into heavier elements such as carbon and oxygen. Later, if the star is massive enough, carbon can fuse as well, followed by still heavier reactions in an increasingly layered interior. The structure becomes stratified, with different forms of fusion proceeding in shells, each one nested around a hotter and denser center. The star resembles a vast engine built in concentric zones, where each inner advance depends on greater pressure, greater heat, and a narrower margin for error. This sequence of fusion stages can sound orderly when described from a distance, but physically it marks a progressive tightening of constraints. Every new fuel is harder to ignite and faster to exhaust. Hydrogen burning can last for most of a star's life, but the later stages pass more quickly, because the balance grows more expensive to maintain. The heavier the element being fused, the more extreme the conditions must be. In a massive star approaching its end, time begins to compress. What once unfolded across millions of years gives way to stages that can be dramatically shorter, until the final structure exists in a state that is both magnificent and unstable. At that point, the star is no longer simply shining. It is resisting collapse through a chain of reactions that cannot continue forever. The crucial detail is that fusion only supports a star while it releases energy. Up to a point, combining lighter elements into heavier ones does exactly that. It produces the outward pressure required to counter gravity. But that logic ends when the core becomes rich in iron. Iron occupies a hard boundary in stellar evolution, because fusing it does not provide the energy the star needs. Instead of helping to support the core, iron marks the moment when support begins to fail. That failure does not unfold with the slow dignity of the earlier stages. Once the core is dominated by iron and fusion can no longer generate useful outward pressure, gravity is no longer balanced by anything comparable in strength. The core begins to collapse. At first this may be described as an implosion, but that word still feels too mild for what actually happens inside such a star. Matter that had existed in a structured stellar interior is suddenly driven inward under a force it can no longer resist. Density rises with extraordinary speed. Temperatures soar. Electrons, which ordinarily occupy a distinct role in atomic structure, are forced into protons. In that violent compression, one form of matter is converted into another. Protons and electrons combine to form neutrons, while neutrinos are released in astonishing numbers. The core does not merely shrink, its physical identity changes. This is the threshold on which the future magnetar depends, because the star is no longer headed toward an ordinary remnant. It is entering the regime where atomic boundaries collapse and matter is stripped down to something far more compressed than the chemistry of everyday reality allows. The collapse accelerates because the core has crossed from controlled burning into runaway compression. Above it, the rest of the star has not yet had time to adjust. The outer layers are still there, still massive, still falling inward once the support from below gives way. The result is a deep mismatch between the inner catastrophe and the surrounding stellar body. When the collapsing core reaches nuclear densities, the inward motion can no longer continue in the same way. The matter becomes incompressible enough to resist further collapse, at least for the moment, and that abrupt resistance helps drive a rebound. The infalling material crashes into that newly stiffened core region, and a shock forms. In a full supernova explosion, the star tears itself apart. What had once been the visible body of the star is hurled outward into space, carrying heavy elements into the interstellar medium and leaving behind only the compact central remnant. This is one of the most consequential endings in astrophysics. It is destructive, but it is also generative. The explosion enriches the galaxy. The remnant becomes one of the densest objects short of a black hole, and in rare cases, under conditions still not fully resolved. That remnant will carry within it the seeds of a magnetar, before the magnetic field grows into something almost unthinkable. The more immediate fact is compression. A stellar core with a mass greater than that of the Sun can be crushed into an object only about the size of a city. That statement is so familiar in popular descriptions of neutron stars that it risks losing its force. But the scale disparity matters because it reveals how completely ordinary intuitions fail at this boundary. The mass remains immense. The volume collapses. Gravity at the surface becomes overwhelming. Density rises to the point that a spoonful of this matter, if it could somehow be removed and kept intact, would outweigh mountains. But even that comparison is only a gesture, because the interior is not a compressed version of ordinary solid material. It is matter driven into a state where atomic structure can no longer survive in any familiar sense. The deeper question is not merely how such matter behaves once formed. The deeper question is how nature reaches that state at all, and how often the collapse leaves behind a remnant stable enough to persist, rather than continuing all the way into a black hole. Magnetars belong to that narrow outcome. They are survivors of a collapse so severe that most of what once defined the parent star has been erased. Seen this way, the birth of a magnetar is not primarily about magnetism, brightness, or danger. It is about a chain of physical thresholds, each one crossed because the previous form of support has failed. Hydrogen runs out, Helium contracts and ignites. Heavier fusion stages follow. Iron accumulates. Pressure disappears. Collapse begins. Electrons and protons are driven together. Neutrons dominate. The outer star is blasted away. A remnant remains. Everything that makes a magnetar strange depends on that sequence being allowed to proceed far enough and fast enough under the right initial conditions. The object that survives is not simply the corpse of a star. It is a record of the moment when stellar equilibrium finally loses its long argument with gravity. That distinction matters because a magnetar is not mysterious in spite of its origin. It is mysterious because of it. The violence of its birth is written into its structure from the beginning, and the next step is to understand what kind of star can emerge from so complete a collapse without vanishing altogether into darkness. The first sign that the core has entered a new form of existence is not light, but escape. In the middle of the collapse, as pressure drives electrons into protons and the internal structure of matter is forced into a denser state, vast numbers of neutrinos stream outward from the dying star. They interact so weakly with ordinary matter that most of them pass through the surrounding layers and into space with little resistance, carrying away an extraordinary share of the energy released in the transformation. This is one of the strangest features of the birth of a neutron star. The most decisive processes do not happen at the surface where a distant observer sees the supernova unfold. They happen in the hidden interior, where atomic matter is pushed so far beyond ordinary conditions that the distinction between familiar substances begins to fail. In that environment, what matters is no longer chemistry, and not even the layered fusion structure that defined the star only moments before. What matters is density, compression, and the rearrangement of the smallest constituents still able to resist total collapse. A magnetar can only exist if that rearrangement produces a stable remnant, and the remnant that emerges is something more severe than any planet, any white dwarf, or any ordinary stellar body. It is matter pressed into a form that belongs less to the usual world of atoms than to the deeper rules that atoms normally conceal. A neutron star is often described as being made mostly of neutrons, and that is true in the broadest sense. But the path to that condition is part of the meaning. Under ordinary circumstances, atoms consist of nuclei surrounded by electrons. Within the nuclei themselves are protons and neutrons, held together by the strong nuclear force. In everyday matter, most of what determines structure, bonding, and physical behavior depends on electrons occupying space around those nuclei. During core collapse, that architecture is broken. The pressure becomes so intense that electrons can no longer remain in their usual states. They are pushed into close contact with protons, and in that contact the particles combine. A proton becomes a neutron, and a neutrino is emitted, repeated across an immense collapsing core. This process changes not just the composition of the matter, but its very regime of stability. The core becomes increasingly neutron-rich, and because neutrons carry no electric charge, the new matter is free from some of the electromagnetic constraints that shape ordinary atomic arrangements. This does not make the matter simple, it makes it unfamiliar. A neutron star is not a giant atomic nucleus in any tidy sense, but there is a reason that comparison returns so often. The same force that binds nuclei now becomes central on a scale vastly larger than any nucleus could naturally reach. What follows is not a smooth settling into equilibrium. The newly formed remnant is born in heat so intense that ordinary words such as hot or molten lose most of their usefulness. Temperatures rise into the tens of billions of degrees. Under those conditions, the matter is not yet the cold, compact object often imagined in textbook diagrams. It is a young neutron star, fresh from collapse, saturated with trapped energy, bathed in neutrinos, and still in the process of becoming itself. That distinction matters because the object that exists in the first instance after formation is not identical to the one that endures for years, centuries, or millennia. The early remnant must cool, it must shed energy, it must survive the violence of its own birth without being pushed over the next threshold into a black hole. The release of neutrinos plays a central role in that survival. In a sense, the remnant is buying its stability by losing energy almost as quickly as the laws of particle physics allow. The supernova is the visible event, but inside it the newborn neutron star is carrying out a far more concentrated negotiation. It is trying to remain a star after the destruction of everything that once allowed the parent star to exist. That effort is governed by a new balance. In the earlier life of the massive star, outward pressure came mainly from fusion. In the neutron star, fusion is over. The support now comes from a combination of nuclear forces and quantum mechanical pressure associated with the extreme compression of matter. Gravity still pulls inward with astonishing strength, but it no longer has unlimited freedom to compress the remnant. The matter has reached densities at which further squeezing meets a different kind of resistance. This is the reason a neutron star can exist at all. If the remaining core is too massive, even these forms of pressure will fail, and collapse will continue toward a black hole. If the mass is within a narrower allowed range, the remnant stabilizes as a neutron star. Magnetars belong inside that fragile category. They are not the inevitable result of stellar death. They are one possible answer to the question of what happens when a massive star collapses, but not quite far enough to disappear behind an event horizon. The surviving object is extraordinarily compact, but it still has a surface, still rotates, still cools, and still carries a history written into its interior. The scale of that interior is one of the central difficulties in understanding neutron matter. A star with a mass comparable to more than the Sun can end as an object only a few tens of kilometers across. That compression drives average densities to values difficult to represent in any intuitive way. Comparisons to mountains, cities, or entire human constructions help only briefly. They tell the mind that something disproportionate has occurred, but they do not reveal what such density means physically. The atoms are gone in their familiar form. The space between nuclei has largely vanished. Matter exists in a packed state where the distinction between one nucleus and the next gives way to a more continuous and collective arrangement. Even then, the interior may not be uniform. The outermost layers remain somewhat more structured, while deeper regions become progressively more exotic. The important point at this stage is that the neutron star is not merely dense in the way a heavy metal is dense. It is dense because the normal hierarchy of matter has collapsed inward. The object is what remains after ordinary atomic structure has been overruled by gravity on a nearly unimaginable scale. Rotation survives this transformation, and in some cases it becomes more dramatic because of it. A massive star already rotating before collapse will spin faster as its radius contracts, in accordance with the conservation of angular momentum. The effect is familiar in principle from much gentler systems, but here it operates under extreme conditions. The remnant can rotate astonishingly rapidly, and that rotation influences everything from its magnetic behavior to the stresses that later build in its crust. At the same time, the object inherits or develops an immense magnetic field. For an ordinary neutron star, that field is already powerful by any planetary or human standard. For a future magnetar, it may become something vastly greater. But before that later distinction matters, the neutron star must first exist as a coherent body. It must retain enough structural integrity to support a crust as it cools, enough internal order to sustain rotation, and enough stability to avoid further collapse. That is why the birth of neutron matter deserved tension on its own. The later magnetism may seem like the main attraction, but magnetism is layered on top of a prior achievement that is in some ways even harder to imagine the survival of a crushed stellar core as a new class of object. There is also a quiet limit built into this process. However extreme a neutron star may be, it is not infinitely flexible. The internal physics sets boundaries on its mass, radius, and composition, and those boundaries remain active scientific problems because the matter involved cannot be reproduced in full anywhere else. Laboratories can probe nuclear physics. Particle accelerators can reveal aspects of dense matter. Observations of neutron stars can measure masses, spins, temperatures, and in some cases infraradii. But the exact behavior of matter at the deepest densities inside such remnants remains only partly constrained. This gives the birth of a neutron star a second kind of mystery. It is not only spectacular as an event, it is also incomplete as a theory. The remnant forms in a domain where gravity, nuclear forces, and quantum pressure all matter at once, and where observation can glimpse outcomes more easily than interiors. What emerges is real enough to detect, measure, and classify. Yet strange enough that even its core composition remains uncertain. By the end of this transformation, the star that once fused element after element in layered shells has become something smaller, harder, and more concentrated than any ordinary intuition permits. Its light no longer comes from a wide, radiant surface powered by sustained fusion. Its future is defined instead by cooling, rotation, magnetic activity, and the slow release of what was locked into it at birth. A magnetar will later distinguish itself by the violence of its magnetic field, by bursts, flares, and starquakes, and by the rare conditions that make it unlike most other neutron stars. But none of that makes sense until the underlying remnant is understood as a body of neutron matter first. The field may become the most visible feature. The deeper fact is that the star has already passed through a more fundamental change. It has crossed from the world of stellar burning into the world of compact matter, where the remnant is no longer supported by fire but by the resistance of matter itself at the edge of collapse. A neutron star can contain more mass than the Sun while fitting inside a sphere only about the width of a city. And that single fact does more than sound strange. It breaks the scale on which ordinary objects are understood. Stars are supposed to be vast. Their size is part of how they are imagined, part of how they hold themselves together, part of how distance softens their violence into points of light. A neutron star keeps the mass but surrenders almost all the volume. The result is not simply a smaller star. It is a different category of object, one in which compression becomes the defining reality. This is the physical ground from which magnetars later emerge. And it matters because magnetars are not merely magnetic stars. They are neutron stars first, built from the same impossible compactness and shaped by the same severe gravity. Before the magnetic field becomes the central question, the scale of the remnant has to be faced on its own terms. A body not much larger than a metropolitan region holds in place a mass that, in the ordinary architecture of a star, once occupied a volume hundreds of thousands of times larger. The shrinking is so extreme that comparison itself becomes unstable. It is like reducing a world of pressure and fire into something the horizon could contain. This compactness is not cosmetic. It determines almost every physical condition at the star. Gravity at the surface is immense because gravity depends not only on how much mass an object has, but on how tightly that mass is concentrated. On Earth, gravity feels familiar because the planet's mass is modest compared with a star and spread across a much larger body than the human scale. On a neutron star, the mass is stellar and the radius is tiny. The surface gravity becomes so intense that anything falling even a very small distance would gain speed with alarming efficiency. Mountains, if they exist there, cannot rise high in the way mountains do on Earth, because the crust cannot support large vertical structures against such weight. Relief is flattened. The surface is forced toward a harsher simplicity. Yet the simplicity is deceptive, because beneath that compressed exterior lies a body carrying more than the sun's mass and holding it in one of the steepest gravitational wells outside a black hole. What matters here is not only that the gravity is strong, but that it acts across such a short distance. The star does not need great size to command its surroundings. Its influence comes from concentration. Light itself must respond to that concentration. General relativity predicts that massive bodies curve space-time, and neutron stars are among the clearest places where this curvature becomes impossible to ignore. A ray of light passing near the surface does not travel in the straight path that intuition expects. It bends. This means that the visible appearance of the star is altered by its own gravity. A distant observer can see more than half the surface at once, because light emitted from regions that would ordinarily be hidden can be curved around toward the line of sight. The star does not present a simple hemisphere to the universe. It presents a distorted version of itself, shaped by the geometry of the space around it. That effect is sometimes compared to the visual warping around a black hole, though the neutron star still has a surface and still allows light to escape. The distinction matters because the neutron star remains visible, measurable, and structured, yet it already lives in a regime where gravity does not merely pull objects downward, it changes how appearance works. Observation itself becomes part of the physics. Density adds another layer to this difficulty. Common comparisons try to make neutron star matter tangible by saying that a teaspoon would weigh as much as a mountain or a civilization's total machinery. Such images are useful only up to a point. They express that the density is extraordinary, but they also risk suggesting that neutron matter is just ordinary material with a great deal more of it packed together. In reality, it is the collapse of ordinary spacing that matters. Most of an atom is empty space in the usual sense. Electrons occupy extended regions around a tiny nucleus, and the distances between nuclei in matter allow familiar solids, liquids, and gases to exist. In a neutron star, those separations are driven almost out of existence. Matter has been squeezed to the point that the distinction between individual atomic systems largely dissolves. Density is not merely a measure of heaviness here. It is the signature of a world where the structure of matter has been forced into a collective state. The star is not built from objects piled closely together. It is built from matter no longer permitted to remain separate in the way everyday substances remain separate. Because of that, even language such as solid or liquid becomes provisional. A neutron star has a crust, and deeper regions may behave in ways that resemble fluids or superfluids, but none of these categories maps neatly onto ordinary experience. The crust is not rock. The deeper layers are not oceans. The star is best understood as a compact remnant whose internal states are determined by pressure, nuclear forces, and quantum effects acting together at enormous density. Still, the crust matters because it gives the object a surface, a place where internal stresses can later accumulate and fail, and a boundary across which radiation escapes. The existence of a crust also highlights the compactness in another way. A star that once existed as a vast envelope of plasma now ends as a body, with a rigid outer shell only a short distance above an interior of extraordinary density. That change in geometry is part of what makes neutron stars feel so severe. They are not diffuse or layered in the generous fashion of ordinary stars. They are abrupt. Surface and depth are brought close together. The descent inward is measured not across hundreds of thousands of kilometers, but across a few tens of kilometers total. While conditions change with startling speed, rotation sharpens the picture further. When the parent star collapses, the remnant can spin rapidly, because angular momentum is conserved as the radius shrinks. Even a star rotating at an unremarkable pace before collapse can leave behind a neutron star spinning many times each second. That rapid rotation has several consequences. It stabilizes some aspects of the object's behavior, contributes to how radiation can be emitted, and helps define the later distinction between ordinary pulsars and the more extreme class of magnetars. But even before those special cases are separated, rotation reminds the observer that the neutron star is not static. It is not a quiet lump of compact matter. It is a dynamic remnant, born, rotating, cooling, and interacting with its own field structure from the beginning. The small size makes that motion more dramatic, because the same physical quantity that once described a huge star now applies to a much smaller body. A large system has been compressed without losing its history of motion. The result is a star that behaves with an intensity out of proportion to its dimensions. The thermal state of such an object also resists easy intuition. A young neutron star is extraordinarily hot, but the heat is distributed through matter so dense and so unusual that the familiar image of glowing metal or incandescent gas becomes inadequate. Most of the energy does not announce itself as visible light in the way an ordinary star does. Neutron stars and magnetars are often best studied through high-energy radiation, including X-rays and gamma rays, because their physical conditions drive emission into more energetic regimes. This makes them harder to imagine directly. The star is compact, dim in ordinary visible terms compared with a main sequence star, but violent in the bands of radiation most human senses never detect. Seen from the wrong perspective, the star could be mistaken for smallness. Seen through its actual physics, it is an environment of pressure, gravity, and radiation far beyond the scale of common celestial objects. The mismatch between appearance and reality is part of its nature. A neutron star may occupy little visual space, yet in physical extremity it stands near the edge of what a stable object can be. There is also a profound threshold quality to neutron stars. They exist just above the line where matter still resists total collapse, and just below the line where a black hole would form. In that sense, every neutron star is a kind of compromise between survival and disappearance. It is matter compressed nearly as far as matter can go, while still maintaining a surface. That gives the object a special status in astrophysics. It is both a remnant and a limit case. It tells science what happens when stellar collapse is almost absolute but not complete. For magnetars, that limit becomes even more important, because the later magnetic field will be generated, sustained, and expressed within a body already living close to the maximum strain of stability. A magnetar is not extreme because it adds magnetism to an otherwise ordinary star. It is extreme because the magnetism is layered onto one of the most compressed stable structures in the universe. The field does not act in empty space alone. It acts through an object already defined by crushing density and relentless gravity. By the end of this view, the neutron star no longer looks like a simple aftermath of explosion. It looks like a compressed stage on which every later magnetar phenomenon must occur. The density sets the pressure. The gravity shapes the surface and bends the light. The small radius sharpens rotation and magnifies the consequences of every internal process. This broader setting matters only because it makes the next question harder, not easier. If neutron stars already live under such extraordinary conditions, then the problem is no longer understanding why they are extreme. The problem is understanding why only some of them cross into something stranger still, where the compact remnant does not merely survive collapse, but emerges carrying a magnetic field strong enough to dominate almost everything else about its existence. In the first moments after a neutron star is born, the object is not yet the rigid, aging remnant it will later become. It is still hot enough for motion to matter in a more fluid and immediate way, still turning with tremendous speed, still carrying within it gradients of temperature, density, and composition left behind by collapse. This brief interval may be where the future of a magnetar is decided. Ordinary neutron stars already possess strong magnetic fields, far beyond anything associated with planets or most stars. But a magnetar appears to cross into a different regime altogether, one where the field is no longer just an important property of the star, but the dominant fact of its existence. The difficulty is that no observer can watch this transformation directly from within the star. What science has instead are theoretical models, indirect evidence, and the later behavior of magnetars themselves. From those clues, one leading picture has emerged. If a newborn neutron star is rotating rapidly enough, and if its interior remains convective and mobile for long enough during the earlier seconds of its life, then those violent internal motions may act like a dynamo, amplifying the magnetic field to extraordinary strength. In that view, a magnetar is not a separate kind of object from the beginning. It is a neutron star whose earliest conditions allow the field to grow into something far more extreme before the interior settles. The underlying idea is familiar in gentler settings. A dynamo is a process by which moving electrically conducting material generates and sustains a magnetic field. Earth has one in its liquid outer core. The Sun has one in its plasma, where rotation and convection help build the magnetic cycles that shape sunspots and eruptions. But scale and mechanism depend on environment, and the environment inside a newborn neutron star is unlike anything found elsewhere in astrophysics. The matter is denser, the rotation may be faster, and the available energy can be concentrated into much smaller dimensions. If rotation is rapid enough, different layers within the star may shear past one another, stretching and winding magnetic field lines. Convection, driven by intense heat and gradients in lepton content left from the collapse, can move charged components through the interior in complex patterns. Even though the star is mostly neutrons, it is not made of neutrons alone. Protons, electrons, and other particles remain present in smaller fractions, and their motion matters because magnetic fields are tied to electrically charged matter. In the right conditions, this churning interior may take a field that is already strong and drive it upward by many orders of magnitude in a very short time. The field does not need millions of years to grow as planetary dynamos do. It may be built in seconds. That possibility makes the birth spin of the neutron star especially important. A rapidly rotating remnant stores enormous rotational energy, and some of that energy may be available to feed magnetic amplification. The difference between a fast newborn neutron star and an ordinary one is not merely a difference in how often it turns. It may be a difference in what the star is able to become before it cools and stiffens. A magnetar is often thought to begin life spinning far more quickly than it does later, perhaps with rotation periods so short that the whole remnant is in a state of severe dynamical tension from the start. Over time, magnetars are observed to spin more slowly, losing rotational energy and evolving into longer periods than many ordinary pulsars. But the present state is not the same as the birth state. What matters is the first interval, when rapid rotation and internal motion overlap. If the star starts too slowly, the dynamo may never push the field to magnetar levels. If it starts fast enough, the field may become so strong that it changes the later evolution of the star altogether. The field then stops being a byproduct and becomes an architect, shaping crustal stress, radiation output, spin evolution, and the violence of future flares. Even this picture is not fully settled. Another possibility is that at least some magnetars inherit powerful magnetic fields from their parent stars. In this fossil field view, the progenitor star already carries an unusually strong field before collapse, and when the core shrinks by an enormous factor, magnetic flux conservation helps intensify that field as the remnant forms. The logic is appealing because collapse greatly reduces the size of the object, and a magnetic field compressed into a much smaller body naturally becomes stronger. But inheritance alone may not easily explain the most extreme observed field strengths, especially if the progenitor field is not already extraordinary. This has left room for a blended interpretation. Perhaps some remnant cores are born from stars with above-average magnetic fields, and also undergo rapid early rotation and dynamo amplification. Perhaps there is more than one pathway. Perhaps the rarest and most violent magnetars emerge where both inheritance and early internal turbulence cooperate. What matters here is not choosing certainty where none yet exists. It is recognizing that magnetar formation is likely a threshold problem. The right mass, the right collapse history, the right rotation rate, and the right internal conditions may all need to align within a very narrow window. This threshold quality helps explain why magnetars are rare compared with the broader population of neutron stars. Most massive stellar deaths do not leave behind remnants with such overpowering magnetic behavior. The neutron star outcome itself already depends on the collapsing core avoiding black hole formation. Magnetar birth appears to require an additional filter. The remnant must survive, rotate rapidly, and perhaps preserve or generate magnetic structure under conditions that many newborn neutron stars do not achieve. That makes the magnetar less like a standard stage of evolution and more like a special branch, a route through stellar death that only some remnants manage to follow. The later lifetime of a magnetar may also be comparatively short in astrophysical terms, not because the star vanishes quickly, but because the most dramatic magnetar behavior is tied to the decay and rearrangement of its immense field. A neutron star may persist for ages, but a magnetar in its most active form may be a more temporary phenomenon, spending only part of its existence in that violent and conspicuous state. This means rarity may reflect both uncommon birth conditions and limited visibility across time. The field itself is difficult to picture because it is not merely a stronger version of an ordinary magnet. It is strong enough to store vast energy in the space around the star and within the star's crust and outer layers. That stored energy becomes central to the magnetar's behavior. In an ordinary pulsar, rotational energy often provides the main reservoir driving the observed emission. In a magnetar, magnetic energy becomes at least as important and in many cases more important. The star can radiate in ways not easily explained by spin alone. It can burst, flare, and undergo episodes of sudden activity because the field is twisting, decaying, and transferring stress into the crust. This is one reason the origin question matters so much. If magnetar fields are built to such enormous strengths at birth, then the star's later life is shaped from the beginning by a reservoir of magnetic energy, unlike that of most other compact remnants. The object is not simply a pulsar with a stronger field, it is a star whose later physics may be dominated by that field in a deeper and more structural sense. There is also the question of where inside the star the strongest field resides. Observations typically infer a large-scale dipole field from spin behavior, but that may reveal only part of the magnetic architecture. The interior may contain even stronger toroidal components, wound around the star beneath the surface, storing energy that later escapes through rearrangement and fracture. If so, the visible field may be only the outer expression of a more complex internal structure. That matters because two stars with similar measured surface fields might still behave differently if their hidden internal configurations differ. It also suggests that the magnetar is not defined by one number alone. Field strength is central, but geometry, depth, and evolution all play a role. A star born with a strong large-scale field and a strong internal toroidal component may be more prone to violent outbursts than one whose field is organized differently. The origin story, then, is not only about how much magnetic energy is created, it is also about how that energy is arranged inside matter, already living under enormous pressure. As the remnant cools, its fluid interior and forming crust begin to lock the consequences of those first moments into place. The star's early dynamical freedom narrows, convection weakens, the crust solidifies, rotation slows. But by then the field may already have been amplified to magnetar scale, and once present it cannot simply be treated as passive. It threads the star, presses on the crust, modifies the magnetosphere, and creates the long tension between stability and release that defines later magnetar activity. In that sense, the birth of a magnetar is not a separate episode from its flares and starquakes. It is the first statement of the same physics. The early star builds a field so intense that the later star must spend thousands of years trying to live with it. Everything observed afterward may be a consequence of that initial excess, frozen into the remnant during the first seconds after collapse. What remains missing is the direct bridge between theory and formation. The dynamo picture is plausible. The inheritance picture is plausible. A combined pathway may be plausible as well. But the interior of a newborn neutron star is hidden, brief in its most decisive phase, and inaccessible to experiment in full. Science can infer the outcome more easily than it can witness the making of it. That difference is what keeps magnetar birth open as a problem. The field is real. The later consequences are real. The exact route by which a collapsing star crosses from neutron remnant to magnetic extremity is still not fully settled, and that unresolved interval is what makes the magnetar feel less like a finished category than an ongoing argument written into matter itself. A pulsar and a magnetar begin from almost the same catastrophe. Each is born from the collapse of a massive star. Each survives only because the remnant core is able to resist total gravitational failure, and each emerges as a neutron star carrying intense gravity, high density, rapid rotation, and a magnetic field far beyond anything familiar in ordinary astrophysical environments. At first glance, that shared origin can make magnetars seem like merely a stronger version of something already known, as though the pulsar is the standard model and the magnetar is simply the louder case. But that impression does not hold for long. The more closely the two classes are compared, the more it becomes clear that they divide not at the moment of birth alone, but in the source of their later behaviour. A pulsar is often governed mainly by rotation. A magnetar is governed increasingly by magnetic energy. That distinction matters because it changes what powers the star, how it evolves, and what kinds of events it is capable of producing. The shared ancestry remains real, but it no longer explains the whole object. Somewhere after formation, or perhaps within the first seconds of it, the future magnetar begins to follow a harsher set of rules. The pulsar is already a remarkable object. It rotates with great regularity and emits radiation from regions associated with its magnetic poles. Because the magnetic axis is often misaligned with the rotation axis, the beam sweeps through space as the star spins. If that beam crosses the line of sight from Earth, the star appears to pulse, not because it is turning on and off, but because the geometry of the beam and the motion of the star create a lighthouse effect. Some pulsars rotate astonishingly quickly, with periods measured in fractions of a second, and their regularity can rival the precision of atomic clocks over certain intervals. This makes them valuable as cosmic laboratories. They reveal relativistic effects, test theories of gravity, and trace the final states of stellar evolution with extraordinary clarity. In most cases, the energy driving that emission comes primarily from the star's rotation. The pulsar is slowing down over time, and a small fraction of its immense rotational energy reservoir is carried away as radiation and particle winds. What keeps the pulsar important is not only the beam itself, but the relation between spin, field, and loss. The star is spending its motion to remain observable. Magnetars can also pulse, They too are rotating neutron stars with strong magnetic fields and misaligned axes that allow periodic radiation to be detected. In that limited sense, the categories overlap. A magnetar may look at first like a peculiar pulsar with a slower spin and a more unruly temperament. Yet the deeper difference is that the magnetar is not primarily powered by its rotation in the same way. Its magnetic field stores such extraordinary energy that field decay, magnetic twisting, and crustal stress become central to the star's observable behavior. A pulsar generally announces itself through steady periodicity. A magnetar may do that as well, but it also bursts, flares, and brightens in ways that rotational spin-down alone cannot comfortably explain. Its timing can become less stable. Its X-ray luminosity can exceed what its rate of rotational energy loss seems able to supply. In other words, the magnetar is not merely rotating and radiating. It is living through the consequences of carrying too much magnetic strain. That is where the shared origin ends and the divergence becomes harder to ignore. Spin period helps illustrate this change, though not by itself. Many ordinary pulsars rotate very rapidly, especially younger ones or those later spun up in binary systems. Magnetars, by contrast, are often observed with comparatively longer periods, typically several seconds rather than fractions of a second. This can seem surprising if rapid birth rotation is part of how a magnetar field is generated, but the paradox is only apparent. If a magnetar begins life spinning extremely quickly and also develops an enormous magnetic field, that same field can break the rotation efficiently. Over time, the star loses angular momentum and its period lengthens. The present magnetar can therefore look slower than a pulsar, not because it was born slow, but because its magnetic field has spent years or thousands of years acting as a powerful brake. This is one reason magnetars and pulsars should not be sorted only by how fast they spin. The surface measurement is a late-stage clue, not the whole biography. A magnetar may be the remnant of a more violent rotational youth than its current pace suggests. The style of emission sharpens the contrast further. Ordinary pulsars are commonly associated with radio waves, though they can emit across a broad range of the spectrum. Their emission is structured, periodic, and closely tied to the electrodynamics of their magnetospheres. Magnetars, on the other hand, are especially prominent in high-energy bands such as X-rays and gamma rays. Some were historically identified as soft gamma repeaters or anomalous X-ray pulsars before the broader magnetar picture unified these categories. That history matters because it shows how the divergence first appeared observationally. The stars did not simply pulse, they erupted. They produced bursts and outbursts inconsistent with a purely rotation-powered interpretation. Their steady X-ray output could be too luminous for their measured spin-down power. Their radiation seemed to come from a different reservoir. Once the magnetic field was recognized as the likely source, a new class of neutron star behavior came into focus. The data did not end the mystery. It changed the shape of it. Instead of asking only how neutron stars radiate, science had to ask what happens when magnetic energy becomes so strong that it reorganizes the entire life of the remnant. Another difference lies in lifetime and visibility. Pulsars can remain detectable for long periods, especially if their emission geometry favors observation and if their rotational energy continues to power coherent beams. Magnetars appear to occupy a more transient and more volatile observational window. Their strongest activity may last only a comparatively brief period in astrophysical terms. Perhaps while the magnetic field is still decaying, rearranging, and loading the crust with stress. This makes them rarer in the sky, not necessarily because neutron stars seldom form, but because only a fraction become magnetars, and because the magnetar phase itself may not remain conspicuous forever. A neutron star can outlive its most dramatic period. The field may weaken. The bursts may cease. The object may come to resemble a quieter remnant. That possibility blurs the boundary slightly, because the neutron star population may contain descendants of ancient magnetars no longer behaving in the classic way. Even so, when magnetars are active, they announce a regime unlike the pulsar norm. Their rarity is not only a census fact, it is part of their meaning. Crustal behavior reveals this difference in a particularly physical form. In an ordinary pulsar, the crust may experience stresses related to spin evolution, glitches, or internal dynamics. But in a magnetar, the field itself can push and twist the crust to the point of fracture. The magnetic lines threading the star and surrounding magnetosphere are not passive structures. They shift, wind, and store tension. When that tension is released, the consequences can be abrupt. Starquakes and magnetospheric reconnection can produce bursts of radiation, from short flashes to giant flares of astonishing energy. This kind of activity is not a minor variation on pulsar behavior. It is a different style of instability. The pulsar is often measured by its clock-like regularity. The magnetar is defined in part by the fact that the clock can be interrupted by violence. Beneath the periodic signal lies a second narrative, one written in fracture, rearrangement, and sudden magnetic release. Yet the categories are not entirely sealed. In recent years, observations have complicated the older picture by revealing some overlap. A few high magnetic field pulsars seem to approach magnetar-like properties, and some magnetars have shown radio emission under certain conditions. This suggests that neutron stars may occupy a broader continuum than the cleanest textbook distinction implies. Field strength matters, but geometry, age, internal structure, and evolutionary history matter as well. There may not be one sharp line where pulsar ends and magnetar begins. Instead, there may be a region of transition, where some neutron stars carry enough magnetic stress to behave partly like one category, and partly like the other. That possibility does not erase the difference. It makes it more interesting. A continuum still contains extremes, and magnetars remain the clearest case of what happens when the magnetic end of the neutron star spectrum becomes dominant. The overlap only shows that nature is less interested in tidy labels than theory sometimes hopes. Seen together, pulsars and magnetars are best understood not as unrelated objects but as neighbouring answers to the same stellar question. What survives after a massive star dies, and the core avoids becoming a black hole? One answer is a rotating beacon, losing energy gradually through electromagnetic emission and particle outflow. The other is a star whose magnetic field grows so strong that it changes the source of the drama. The pulsar and the magnetar share mass, density, and compactness. They share the physics of neutron matter and relativistic gravity. But the magnetar carries an excess, and that excess reshapes everything. The deeper question is not merely why it emits more energetically. The deeper question is what it is like for matter already compressed almost to the edge of collapse to live under a magnetic field strong enough to rival the structure of the star itself. That is the threshold where the comparison with pulsars becomes less about taxonomy and more about consequence. Because from there, the magnetar begins to look less like a variant of neutron star behavior and more like the place where neutron star physics starts to exceed its own ordinary limits. Light reaches a magnetar only after passing through a gravitational landscape harsh enough to alter the path of sight itself. This is one of the first ways the object resists ordinary intuition. A star may be imagined as something that can be looked at from outside, with one hemisphere facing the observer and the rest hidden beyond a clean horizon. That assumption works well enough for many bodies in space, where light travels away from the surface in almost straight lines, and the visible edge marks a simple limit. A magnetar does not preserve that simplicity. Its mass is packed into such a small volume that the surrounding space-time is strongly curved. and the light leaving the surface must travel through that curvature before it can escape. The result is subtle in description but profound in implication. The star does not merely shine, it presents itself through a distorted geometry, and the distortion is so strong that more than half of the surface may become visible at once. In that sense, the magnetar cannot be seen in the ordinary way because the act of seeing has already been modified by the gravity of the object being seen. This bending of light is a direct consequence of general relativity, but in a magnetar the abstraction becomes almost tangible. The surface lies only a short distance above a gravitational field strong enough to force light into noticeably curved trajectories. A photon emitted from the far side of the star may not continue outward in the direction first expected. Instead, its path can arc around the compact remnant and still arrive at a distant detector. That means the visible limb of the star is no longer the true boundary between what is seen and what is hidden. Regions that would disappear on an ordinary sphere remain partly in view. The star exposes more of itself than geometry alone would allow. This does not mean the entire surface becomes visible at once, nor does it remove all mystery from the remnant, but it does mean that observation begins with an optical condition already shaped by extreme gravity. The magnetar is not hiding behind darkness. It is hiding behind curvature, and curvature gives back only a distorted version of the truth. What matters here is that the distortion is not decorative. It changes how brightness is interpreted, how emission regions are modelled, and how the star's rotation is reconstructed from pulses. If a hotspot exists on the surface, perhaps where magnetic activity concentrates heat, the way that hotspot appears to brighten and fade during rotation depends not only on its position and the star's spin, but on how strongly the light is bent on its way outward. A region near the edge of the visible disk may remain observable longer than expected, because gravity keeps some of its light within view. This can smooth pulses that would otherwise appear sharper. It can change the contrast between bright and dim phases. It can complicate the attempt to infer the size, location, and temperature of emitting regions. In other words, the magnetar's gravity does not simply make the star difficult to escape. It makes the star difficult to read. Every observation arrives already filtered through a strong field of interpretation, where appearance and structure can no longer be separated cleanly. There is another consequence as well. Light climbing away from the surface of a magnetar loses energy as it escapes the deep gravitational well. This is gravitational redshift, a process by which the wavelength of the emitted radiation is stretched on its outward journey. The radiation still carries information about the surface and the outer layers, but it does not reach distant instruments unchanged. Its energy has been modified by the same compactness that bends its path. This matters especially in the study of X-ray spectra, where subtle features may contain clues about the surface temperature, magnetic environment, and composition of the outermost layers. If the gravity is strong enough to shift the outgoing light significantly, then what is measured far away must be translated back through theory to estimate what was actually emitted. The magnetar is therefore not only a source of radiation, it is a source whose own gravity edits the message before the message leaves. That editing becomes more complex when magnetic effects are added. A magnetar is not only compact, it is also threaded by a magnetic field so intense that the space immediately around it becomes a region where radiation, particles, and field structure interact in ways unlike those found around ordinary stars. The emission observed from a magnetar often comes from its surface and magnetosphere together, not from a quiet spherical photosphere in the familiar stellar sense. Thermal radiation can emerge from the hot crust, while additional higher energy components may be shaped by particles moving along magnetic field lines above the surface. Seen at planetary scale, light appears straightforward. Seen near a magnetar, even the boundary between where light originates and how it is altered becomes harder to defend. Gravity bends the path. The magnetic field shapes the environment through which that path passes. Observation becomes less like looking at a surface and more like reconstructing an event in layered stages. This is one reason magnetars are rarely imagined from visible light alone. To human eyes, if one could somehow observe safely and clearly, the surface might not appear as dramatic as the physics demands. Its thermal emission is concentrated heavily in the X-ray range because the surface is extraordinarily hot, far hotter than most ordinary stars are at their visible surfaces. A magnetar may emit some visible light, but that is not where most of its power announces itself. The remnant is more naturally a high-energy object, best known through instruments sensitive to X-rays and gamma rays rather than through conventional optical telescopes. Even here, gravity remains part of the puzzle. A bright X-ray source seen from afar is not simply glowing. It is revealing conditions at a surface compressed so tightly that both the colour and the path of its light have been changed before arrival. The object appears not as it is in isolation, but as it is after surviving its own field of distortion. Rotation complicates the picture once again. Many magnetars are observed as pulsing sources because bright regions, magnetic asymmetries, or magnetospheric structures rotate in and out of view. Yet because gravity allows more of the surface to remain visible at once, the pulse profile is not a simple alternation between full view and concealment. Light from regions near the edge can linger. Emission from the far side may contribute. The surface itself may not be uniformly bright, especially after bursts or during active phases when heating can become localized. The pulse then becomes a composite signal shaped by geometry, relativistic bending, surface temperature distribution, and the star's magnetic architecture. A slow, repeating modulation may seem easier to interpret than a sudden flare, but in some ways it poses the deeper challenge. The pulse is not merely a clock, it is a map distorted by extreme gravity, and reading it correctly requires knowing how the distortion works. The magnetar's small size also contributes to a peculiar visual severity. A larger star can have atmospheres, extended envelopes, and gentle transitions between interior process and outward appearance. A magnetar has little room for such softness. Surface and surrounding magnetosphere are brought close together. The radius is so small that the gravitational field steepens rapidly just outside the crust, and this makes the optical environment unusually compressed. Light does not have far to travel before confronting a major change in gravitational potential. The result is a kind of observational immediacy. The magnetar looks remote because it is far away in space, yet its visible behaviour is dominated by processes occurring across distances smaller than a city. This contrast is part of its strangeness. Something so compact produces signatures that travel across the galaxy. But those signatures are born in a region where every kilometre matters and where the difference between surface and near space is physically enormous. There is also a more philosophical consequence to this curved visibility. Most astronomical objects are studied under the assumption that observation, while imperfect, can be conceptually separated from the object itself. One can account for dust, distance, detector sensitivity, or orbital alignment. But the object remains a thing out there whose light mostly reports its state. A magnetar narrows that separation. The object's own gravity becomes one of the main reasons the report is difficult to interpret. The remnant not only emits radiation, it rearranges the angles, energies, and visibility of that radiation in transit. In a quiet way, this makes the star feel more self-enclosed than many other bodies in astrophysics. It cannot be looked at without also looking through its compactness. The observer never meets the surface directly. The observer meets a version of the surface already bent by the mass beneath it. That distinction matters because it prepares the way for the more violent features of magnetars without yet invoking them. Before the giant flares, before the starquakes, before the magnetic field begins twisting the surrounding vacuum into stranger optical behavior, the star has already established one essential fact. It lives in a region where ordinary sight fails. The visible face is not the whole face. The emitted energy is not the received energy. The geometry of the surface is not the geometry of the image. Everything observed so far can be arranged into a plausible picture of a compact, hot, rotating star whose gravity forces light into unusual paths, but not yet into a settled one, because every surface feature is interpreted through distortion from the start. By the end of that chain of reasoning, the magnetar no longer appears merely bright or dense. It appears as a star whose appearance itself is unstable under the weight of its own gravity, and that is only the beginning of what its outer layers still have to reveal. From far away, a magnetar can seem almost disciplined. Its light may pulse with repetition, its surface may be represented as a compact sphere, and the violence associated with it may appear to belong mainly to bursts that happen only now and then. But that impression depends on distance. Up close, the outer skin of a magnetar is not a quiet boundary between star and space. It is a rigid, overheated crust lying over an interior of extraordinary density and beneath a magnetic field that never stops pressing on it. This is one of the harshest surfaces known in astrophysics, though surface is only partly the right word. On an ordinary star, the visible exterior is often a fluid atmosphere, a luminous layer with no fixed shell beneath it. A magnetar is different. As it cools from the inferno of its birth, its outermost regions solidify into a crust only a relatively short distance above much stranger matter below. That crust is not rock in any earthly sense, yet it behaves as a solid lattice under immense compression, carrying the burden of the magnetic field and the weight of everything deeper inside. What makes it so important is that the crust does not merely cover the star. It records strain, channels heat, and eventually fails. The temperature at the surface remains extreme by any ordinary standard. Even long after formation, a magnetar can have a surface temperature of millions of degrees, far hotter than the visible surface of the sun. Yet the meaning of heat here is not the same as in a common flame or a furnace. The star is small, dense, and radiating much of its energy in X-rays rather than visible light. So the surface does not resemble a familiar glowing body. Its heat is bound up with deep internal energy, magnetic decay, and the conduction properties of matter compressed beyond normal atomic behavior. This is why the surface can remain so energetic even when rotation alone would not seem enough to sustain such a mission. The crust is not simply cooling from the original collapse. It is also being fed, in part, by the slow rearrangement and dissipation of magnetic energy within the star. That extra source matters because it makes the magnetar's exterior more restless than a passive cooling remnant would be. A neutron star without such an overwhelming field can still be hot and still emit X-rays. But in a magnetar, the field becomes an added engine of surface activity. Because the temperature is so high, most of the radiation leaving the outer layers lies beyond human sight. The surface is best imagined not as red-hot or white-hot in the everyday sense, but as radiating in an energetic band where detectors, not eyes, do most of the seeing. Even so, if translated into visible impression, the surface would likely appear pale, almost white, because of the combination of emitted wavelengths. That whiteness would be misleadingly calm. It would suggest uniformity where the physics instead supports gradients, hot spots, and regions of shifting stress. A magnetar surface is not guaranteed to radiate evenly. Magnetic geometry can guide heat through the crust unequally. Certain areas may be hotter than others, especially after outbursts or during intervals when magnetic twist in the outer magnetosphere channels returning particles down to the surface. This can create bright patches that rotate in and out of view, contributing to the pulsed X-ray signals observed from Earth. What looks like regularity in the light curve may therefore be rooted in a landscape of uneven heating written into the crust by magnetic structure. The crust itself forms because the outer layers of the neutron star cool enough to settle into an ordered arrangement of nuclei immersed in a sea of electrons. Yet even this seemingly simple description hides something extreme. The nuclei are not arranged under ordinary pressures. They are packed together in a gravitational field so severe that the spacing between structures is driven far beyond terrestrial comparison. As depth increases, the nuclei become increasingly neutron-rich, adjusted by pressure into forms that cannot persist in ordinary matter. Electrons move through this environment under conditions of enormous degeneracy, and below the outer crust the distinction between intact nuclei and free neutrons begins to blur. The deeper one goes, the more the crust approaches the threshold where matter ceases to resemble a lattice of compressed ions and becomes instead a more continuous neutron-dominated medium. But the outer crust remains crucial because it is the part that can crack. It is the mechanical skin of the star, thin in proportion to the whole object, yet strong enough to support stress, until the stress exceeds what even such matter can bear. That strength is one of the stranger facts about neutron star crusts. Under such pressure, the crust may be among the strongest known materials in the universe, not because of chemistry in the familiar sense, but because the nuclei are held in place under immense compression and gravity, suppresses many of the fractures and voids that weaken ordinary solids. Yet strength does not guarantee tranquility. In a magnetar, the crust is threaded and strained by magnetic fields so intense that even this extraordinary rigidity can become a liability. A strong crust can store more stress before yielding. That means energy can accumulate. The field below and above the crust may evolve, twist and drift, trying to force the solid outer layer into new shapes it cannot easily adopt. For a time the crust resists. It bends, not visibly in the human sense, but in the physical sense of supporting elastic strain. Eventually the stress may exceed a threshold. When that happens, the crust can fracture or shift abruptly, and the consequences may race outward through the magnetic field in the form of a burst. Before those failures occur, however, the surface gives little away. The scale of the star is so small and the gravity so strong that relief is suppressed. Mountains, if they can be called that, would be tiny by earthly standards. Perhaps no more than slight irregularities in a shell otherwise forced toward near spherical form. Gravity pulls every feature down. The crust cannot rise far because even a slight vertical deviation carries immense weight. This means the surface of a magnetar is not dramatic in the topographical sense. It does not need cliffs or towering ridges to be severe. Its violence is internal and structural. The important differences are not measured in grand visible terrain but in temperature, composition, field geometry, and stored strain. A quiet-looking surface can therefore conceal an extraordinary imbalance. The star seems smooth, not because it is relaxed, but because gravity leaves it little choice. The outermost layers may also support a thin atmosphere, though not in the generous planetary sense. Any atmosphere above a magnetar would be shallow and dominated by the magnetic field, gravity, and high temperature. Atoms there may behave in distorted ways, stretched and constrained by field strength that alter their normal electronic structure. Radiation travelling through such a layer can pick up spectral features that offer clues to the local conditions, though interpreting those clues is difficult because gravity, magnetic effects, and uncertain composition all complicate the signal. Even so, the existence of any atmosphere or envelope above the crust matters because it forms the immediate interface between the star and its magnetosphere. Particles can be accelerated there, Heat can be redistributed, emission can be scattered and polarized. The magnetar does not end sharply at the crust. It transitions into a magnetic environment that is intimately tied to whatever happens below. This makes the crust a mediator as much as a boundary. It lies between the hidden interior and the active magnetosphere, translating slow internal evolution into outward consequences. Heat from within can diffuse through it. Stresses from magnetic reconfiguration can load it unevenly. Its conductivity helps determine how temperature spreads across the surface. Its rigidity determines how long the star can endure strain before it releases it suddenly. In that sense, the white crust of fire is not merely the top layer of the star. It is the stage on which the star's deeper contradictions become visible. Below it lies matter close to the edge of theoretical understanding. Above it lies a magnetic domain that can flash into high-energy activity. The crust must live between those worlds, rigid enough to hold shape, fragile enough to fail, hot enough to shine, and stressed enough that its apparent calm can never be trusted for long. What follows from that condition is not immediate destruction, but stored possibility. A magnetar crust can remain intact while the field continues to evolve beneath and around it. The star can pulse steadily, radiate in X-rays, and appear almost orderly for long periods. Yet the order is conditional. The field is too strong, the crust too burdened, and the geometry too severe for equilibrium to mean safety in any ordinary sense. The surface may look smooth, the light may look periodic, the temperature may suggest only a hot compact remnant cooling in space. But the real condition is more exacting than that. The crust is under load. Every hot spot, every pulse shape, every shift in emission hints that the outer shell is not a passive skin but a pressured structure, waiting for magnetic stress to exceed what matter can bear. By the end of this view, the surface no longer looks like the end of the star. It looks like a threshold, a rigid and radiant limit under which strain is gathering, and once that strain breaks through, the magnetar's calm exterior will cease to be the main story at all. The first visible sign that a magnetar is under too much strain may be over almost before an observer realizes it has begun. A sudden flash appears in X-rays or gamma rays, brief yet intense, sometimes lasting less than a second, sometimes followed by a longer fading tail, and the compact star that had seemed like a difficult but stable source now reveals a second character entirely. These events are often described as bursts or flares, but those words risk sounding softer than the underlying process. A magnetar does not erupt in the manner of an ordinary star whose outer layers boil and convect on a large luminous surface. It releases stress from a rigid crust and a twisted magnetic field, both of them carrying stored energy built up over time inside a body already compressed to an extreme degree. The burst is therefore not just an emission event. It is the moment when a long internal argument between solidity and magnetic force is resolved abruptly, and because the field is so immense, even a short release can exceed the energy of more familiar astrophysical processes by astonishing margins. This is where the magnetar ceases to be merely a compact remnant with an unusual field and becomes one of the most violent laboratories in the known universe. The idea of a starquake offers a useful way into this process, though it should be understood carefully. The comparison to an earthquake is appealing because both involve a rigid outer layer storing stress and then releasing it suddenly through fracture or slippage. On Earth, tectonic plates shift under stresses generated by the slow motion of the planet's crust and mantle. In a magnetar, the scale, material, and cause are entirely different, yet the logic of stored strain remains. The crust is immensely strong, but it is also burdened by a magnetic field that is evolving beneath it and through it. If the internal field slowly shifts, twists, or decays, it can impose changing stresses on the solid outer layers. For a time, the crust responds elastically. It deforms slightly while maintaining coherence. Eventually, however, the stress may exceed what even this extraordinary material can support. At that point, the crust may crack, yield, or rearrange. The starquake is not important because matter breaks in a dramatic, metaphorical sense. It is important because the crustal failure can couple directly to the magnetic field around the star, sending energy outward with remarkable speed. Another path may involve the magnetosphere itself becoming unstable. The magnetic field lines above the surface can twist and store energy in the surrounding space, somewhat as stressed field lines do in solar flares, though here under far more extreme conditions. If that magnetic structure becomes too distorted, reconnection can occur, rapidly converting magnetic energy into heat, particle acceleration, and radiation. In practice, the distinction between crustal fracture and magnetospheric instability may not always be clean. A stressed crust can shift and drive a change in the field. A twisted field can push back on the crust until it yields. The flare may therefore be the surface expression of a deeper coupled system rather than a single isolated trigger. This matters because it means the burst is not simply a surface event or simply an atmospheric one. It is a release of stress across the interface between the star's solid exterior and the magnetic domain around it. The crust provides the rigidity, the field provides the stored energy and the means of rapid transfer. Together they create a system in which long preparation can end in a brief and spectacular discharge. Most magnetobursts are relatively short and modest compared with the largest possible events, though modest is a difficult word in this setting. Even minor bursts can outshine many ordinary sources in the high-energy sky for a brief interval. Then there are intermediate flares, larger and more energetic, and beyond those the rare giant flares that define the magnetar at its most extreme. In a giant flare, an initial spike of gamma rays can release an immense quantity of energy in a fraction of a second, followed by a decaying tail modulated by the star's rotation as trapped fireballs of plasma and radiation interact with the magnetic field. These are among the most dramatic non-terminal events known from neutron stars. The star is not destroyed, it remains in place. Yet for a brief moment it can radiate with a ferocity that reaches across the galaxy. The event does not need long duration to be consequential. The power is in the concentration. A magnetar can spend years storing magnetic stress, and then discharge part of it in an instant that briefly dominates the high-energy sky. One of the clearest demonstrations of this came from a giant flare detected from the magnetar known as SGR 1806-20. The source lies far across the galaxy, yet the flare it produced was so intense that it became one of the brightest extraterrestrial high-energy events ever recorded at Earth. The energy released in a tiny fraction of a second rivaled what the Sun produces across a vast span of time. That comparison is not useful merely because it is large. It is useful because it reveals the compression of the event. An ordinary star radiates by sustaining fusion across an enormous surface for ages. A magnetar flare releases stored magnetic energy from a body only a few tens of kilometers wide, and it does so almost instantaneously. The scale mismatch is part of what makes the phenomenon so unsettling. The source is tiny. The consequences are galactic. A distant instrument does not need to be nearby to register that something extraordinary has occurred. The flash arrives across tens of thousands of light years and still forces attention. This naturally raises the question of danger. A magnetar is not a practical threat to Earth in its known present distances, but the physics leaves little doubt about what proximity would mean. A sufficiently nearby giant flare could damage the atmosphere of a planet by delivering intense gamma radiation, capable of altering chemistry high above the surface. Ozone depletion is often discussed in this context because gamma rays can drive reactions that reduce the protective ozone layer, increasing the penetration of harmful solar ultraviolet radiation afterward. The effect would not need the magnetar itself to move close in any ordinary sense. It would only require a giant flare to occur at a sufficiently short astronomical distance. Fortunately, known magnetars are far enough away that such an event is not part of the immediate terrestrial future. But the possibility matters as an illustration of scale. The burst is not only bright in the abstract observational sense, it is powerful enough that, under the wrong circumstances, it could have planetary biological consequences far from the star itself. What appears at first as a burst in a detector is, in physical terms, a sudden exposure of how much energy a magnetic field can store when wrapped around compact matter. Even without considering distant planetary effects, the local environment around a flare would be forbidding. Particles can be accelerated to high energies. Radiation fields become intense. The magnetosphere may fill with a pair plasma of electrons and positrons held in place by magnetic confinement for part of the event. The surface itself can be heated. The crust may continue to adjust after the initial release, producing aftershocks in the form of smaller bursts or prolonged emission changes. In some giant flares, oscillations detected in the fading tail have been interpreted as possible signatures of seismic vibrations in the star, as though the remnant continues ringing after the main fracture. This is especially important because it suggests that a flare may briefly allow the hidden structure of the star to speak through timing patterns. The burst is destructive in one sense, but scientifically it is also revealing. A crust under enough stress to crack may momentarily expose information about the coupling between surface, interior, and magnetic field that is otherwise difficult to obtain. The magnetar becomes brightest at the moment it is least stable. There is a deeper consequence to all this. A flare is not an isolated spectacle added onto an otherwise ordinary star. It is evidence that the magnetic field is strong enough to compete with the structural integrity of the remnant itself. In many astrophysical systems, fields matter, but they do not dominate the architecture of the object to this extent. In a magnetar, the field can load the crust, shape the magnetosphere, power the persistent X-ray emission, and then, when the stored tension becomes too great, tear through equilibrium in a burst. The flare is therefore a diagnostic of the star's whole condition. It tells science that the object is not simply cooling and spinning down in peace. It is trying to inhabit an internally contradictory state, rigid yet strained, compact yet unstable in its outer layers, quiet for long intervals yet always carrying the possibility of sudden release. The burst is the visible proof that this contradiction cannot be resolved smoothly. By the end of such an event, the star has not become simpler, it has become more difficult. A giant flare confirms that magnetic stress can overpower crustal stability, but it does not fully settle whether the initial trigger lies deeper in the crust, higher in the magnetosphere, or in a coupled failure between both. The energy scale is suggestive. The timing is suggestive. Even the oscillations that follow are suggestive. What remains missing is the one kind of evidence that would let observation watch the chain of failure unfold from beginning to end. For now, the flare is both an answer and a sharper question. It proves that the magnetar can crack under its own field, and in doing so it directs attention below the surface, where the remnant's deeper structure must be carrying more of the story than the burst alone can show. Just beneath the crust, a magnetar enters one of the strangest material regimes ever proposed in astrophysics. A region where the pressure is so immense that matter is forced into organized shapes, with names borrowed from food, only because ordinary language has almost nothing better to offer. The terms are playful, but the physics is severe. Here, atomic nuclei are no longer arranged in the relatively regular lattice of the outer crust. They are pushed so close together and loaded with so many neutrons that the distinction between separate nuclear islands and a more continuous medium begins to fail. Density rises sharply with depth. Electrons are still present, but the nuclei themselves become progressively distorted under the competing demands of nuclear attraction and electric repulsion. Matter is trying to minimize its energy while trapped inside an environment where gravity has stripped away almost every familiar option. The result may be a sequence of intermediate forms, each one more difficult to imagine than the last, in which the internal architecture of the star briefly becomes ordered not by chemistry in the ordinary sense, but by geometry under crushing force. The transition begins in the inner crust, below the outer layers where nuclei still retain a more recognizable integrity. As pressure increases, the nuclei absorb more neutrons than stable matter on Earth could ever hold. Eventually they become so neutron-rich that they can no longer contain all those neutrons inside their boundaries. Some leak outward, forming a background sea of free neutrons surrounding the nuclear structures. This is an important threshold because the crust ceases to be made only of nuclei and electrons. It becomes a mixed environment, part lattice and part neutron fluid, with properties that depend on both. The nuclei remain as dense clusters, but they are no longer isolated. They are embedded in matter already halfway toward the deeper continuous phases below. That arrangement is not an incidental curiosity. It changes how heat moves, how the crust vibrates, how magnetic stresses may be transmitted, and how the star responds when its outer layers are pushed toward failure. The crust becomes less like a shell of exotic solid matter, and more like a frontier region between ordinary nuclear identity and something much harder to classify. It is in this frontier that nuclear pasta is thought to emerge. The name refers to a family of predicted shapes that matter may adopt when the density becomes high enough that spherical nuclei are no longer the lowest energy solution, yet not so high that all structure disappears into a uniform core. In this regime, the strong nuclear force, which tries to bind matter together at short range, competes with the electric repulsion of protons, which resists too much concentration of charge. Under ordinary conditions, nuclei settle into compact forms. Under magnetar crust conditions, the balance shifts. Spheres may become elongated rods. Rods may merge into slabs. Slabs may fold, tunnel, or invert into patterns where voids run through denser matter, rather than dense matter standing apart in emptier space. The playful labels of gnocchi, spaghetti, and lasagna are attempts to describe these possible geometries, but what matters is not the resemblance. What matters is that matter in this region may organize into large-scale nuclear structures unlike anything stable in the wider universe. The star briefly contains a hidden architecture built from the deformation of nuclei themselves. This region is not important merely because it is strange. It matters because its structure could affect the star's behavior in measurable ways. A layer of nuclear pasta may be exceptionally rigid or unusually good at resisting shear, which would influence how stresses move through the inner crust. It may alter thermal conductivity, shaping how heat from the deeper interior reaches the surface. It may affect neutrino emission during the early life of the neutron star, changing how efficiently the remnant cools. It may even play a role in the star's oscillations, glitches, or the detailed dynamics of crustal fracture. In the magnetar, where magnetic strain loads the crust continually, the inner crust is not a passive foundation. It is part of the mechanism by which the outer shell either endures or fails. A stronger inner lattice can store and transmit stress differently from a weaker one. A more complex geometry can scatter motion, trap heat, or modify how the crust couples to the fluid layers below. The pasta phase therefore matters not because it adds exotic flavor to the story, but because it may quietly control how the star lives with its own extremity. Deeper still, the structured region gives way to something more uniform. the nuclei dissolve as separate entities, and matter becomes dominated by a dense fluid of neutrons with a smaller population of protons, electrons, and perhaps other particles mixed in according to the local pressure and energy balance. This is the outer core, though outer is a relative term inside an object only a few tens of kilometers across. The physical difference from the crust above is profound. Rigidity gives way to fluid response. The free neutrons may enter a superfluid state, moving without ordinary internal friction under the right conditions, while the protons may become superconducting, allowing electric currents to persist in unusual ways and changing how magnetic flux is arranged inside the star. These are not decorative theoretical additions. They are among the best reasons neutron stars are treated as laboratories for matter under conditions unattainable elsewhere. A superfluid interior does not behave like a simple fluid in a container. It rotates through quantized vortices. A superconducting proton component does not merely carry charge. It may channel magnetic flux into discrete structures, modifying how the internal field evolves and how it communicates stress to the crust. For a magnetar, this becomes especially significant. If the core contains superfluid neutrons and superconducting protons, then the immense magnetic field may not spread through the interior in a smooth, ordinary way. Instead, it may be threaded through flux tubes, coupled imperfectly to neutron vortices associated with rotation, and tied into the long-term evolution of the star in ways still not fully understood. This means the core is not simply a dense reservoir beneath the crust. It may be an active participant in the star's magnetic history. The decay of the field, the migration of magnetic stress, and the timing of surface outbursts could all depend in part on how the interior components interact. A crust can crack only after stress has been supplied to it, and some of that stress may originate in the hidden magnetic architecture of the core. In that sense, the visible burst at the surface may begin much deeper down, in a slow internal rearrangement moving through matter that behaves according to quantum rules on a macroscopic scale. Then comes the deepest uncertainty of all. At still greater densities, the matter in the inner core may undergo further transitions that are not yet established with confidence. Some models suggest the appearance of hyperons, particles containing strange quarks, once pressure becomes high enough to make them energetically favourable. Others allow for meson condensates or for a more radical possibility in which the neutrons and protons themselves cease to remain the right degrees of freedom and the core becomes deconfined quark matter, a state where quarks move less as bound components of individual nucleons and more as part of a collective dense medium. Among the most speculative versions of this idea is strange quark matter, in which up, down, and strange quarks coexist in a stable or metastable phase deep inside the star. No such state has been confirmed in a magnetar, and perhaps it never forms in nature at all. But the possibility persists because the densities involved are so high that the familiar boundaries of nuclear matter may not be final. The question is not idle. Different inner core compositions would change the star's maximum mass, radius, cooling behavior, and oscillation spectrum, and might influence how magnetic energy is stored and transported through the remnant. This is why the interior of a magnetar remains one of the most challenging places in modern physics. It cannot be sampled directly. It cannot be reproduced in full in terrestrial laboratories. Its properties must be inferred from masses, radii, cooling curves, pulse shapes, burst behavior, and occasional hints carried outward through seismic oscillations or gravitational effects. The star reveals the consequences of its interior more easily than the interior itself. A burst may hint at crustal strength. A timing irregularity may suggest superfluid motion. A radius estimate may narrow the allowed equations of state, the relations that connect pressure and density inside the star. But none of these clues yet resolves the full structure from crust to centre. The magnetar remains an object whose outermost kilometre may already contain phases of matter unknown on Earth, while its central regions may lie beyond even the best constrained theories of dense nuclear physics. Every layer is a boundary between what is modelled and what is known. Seen as a whole, the magnetar interior is less like a single material than a descending sequence of compromises forced by pressure. The crust begins with compressed nuclei in a rigid lattice. The inner crust introduces free neutrons and deformed nuclear structures. Nuclear pasta appears where shape becomes the least costly solution to impossible crowding. The outer core dissolves the remaining lattice into a dense neutron-dominated fluid, perhaps threaded with superconducting protons and governed by superfluid dynamics. The inner core may push further still, toward particles and phases rarely encountered even in theory outside the densest compact stars. Each layer exists because the one above can no longer remain stable under the weight below. That is the deeper logic of the magnetar. Its violence at the surface is only the visible expression of a body built from successive failures of ordinary matter to remain ordinary, by the time the descent reaches the centre. The question is no longer what the star is made of in the simple sense. The question is how many times matter has had to reinvent its own structure just to keep the remnant from collapsing further into silence. The magnetic field of a magnetar is often introduced through comparison. Earth has a magnetic field strong enough to guide compasses and shape auroras, yet that field is gentle. Laboratory magnets can be far stronger, but a magnetar belongs to another scale. Its field is so far beyond planetary and human experience that the word strong begins to lose precision. What matters is not only that the field is larger by many orders of magnitude. What matters is that at magnetar strength, magnetism ceases to be a background influence and becomes a governing condition for the behavior of matter, radiation, and the space immediately surrounding the star. A magnetic field of that size is no longer just something that acts on magnets or charged particles in familiar ways. It becomes one of the main structural facts of the environment, capable of constraining atoms, loading the crust, and storing enough energy to power some of the most violent bursts known from compact stars. On Earth, magnetism usually enters life modestly. It aligns a compass needle, guides electrical machines, and records information in old magnetic media. Even powerful industrial magnets remain local objects. Their influence is impressive but limited. A magnetar field is different not simply because it is stronger, but because it crosses thresholds where ordinary material behavior begins to change qualitatively. Electrons moving through atoms and solids respond to magnetic fields. Yet under common conditions, those responses are small compared with the electrostatic forces that define atomic structure. Near a magnetar, the field becomes strong enough that this hierarchy is disrupted. The field can compete with, and in certain respect dominate the internal scales that normally shape atoms. In that regime, matter is not merely placed inside a magnetic field. Matter is forced to exist under magnetic conditions so extreme that its usual shapes and energies are no longer the natural ones. A magnetar is not just surrounded by magnetism, it is embedded in a magnetic order severe enough to rewrite what ordinary matter is allowed to do. This becomes clearer when considering distance. The field close to the magnetar is vastly stronger than the field farther away, and because the star itself is compact, the near-field region is physically abrupt. The field remains impressive, but it no longer dominates the detailed structure of matter in the same catastrophic way. Closer in, however, the gradient becomes unforgiving. Any normal material approaching the star would encounter an environment in which magnetic forces can overwhelm chemical bonds and structural integrity. The common description that a magnetar could tear matter apart atom by atom is dramatic, but it points toward a real physical problem. different parts of an extended object would experience different magnetic stresses. Charged constituents within atoms and molecules would be forced into unfamiliar alignments. The field would not merely attract or repel, it would impose an entirely different balance of forces throughout the object. Long before anything touched the crust, ordinary material identity would already be under assault. Atoms in such a field are among the clearest examples of this altered hierarchy. In normal conditions, atoms are roughly spherical in their electronic probability structure, or at least organized according to quantum states that retain a certain symmetry around the nucleus. Under a magnetar scale field, those states are drastically modified. Electron motion perpendicular to the field is tightly constrained, while motion along the field remains less restricted. The result is that atoms can become elongated, drawn out along the magnetic direction into narrow structures unlike their usual forms. Chemistry, which depends on how electrons occupy orbitals and share space between atoms, would therefore cease to behave normally. Bonds could be altered or suppressed. Matter might organize in chain-like ways favored by the field rather than by ordinary three-dimensional electronic structure. The field does not merely threaten life or technology by brute strength. It changes the quantum landscape from which chemistry itself is built. Charged particles are even more directly constrained. Electrons and ions spiral around magnetic field lines, and in strong fields their motion across those lines becomes increasingly difficult. This channels particles into narrow paths, shapes currents in the magnetosphere, and helps trap plasma in structures above the surface. The field also stores energy in those twisted structures, which is part of why magnetars can flare so violently when the configuration becomes unstable. Magnetic pressure in this context is not a metaphor. It is a real component of the surrounding environment, capable of competing with matter and radiation as a source of force and order. In many astrophysical settings, magnetic fields matter but remain secondary to gas pressure, gravity, or orbital motion. Around a magnetar, the field can dominate the local plasma dynamics so completely that it becomes the main language in which the environment is organized. The effect on technology is easier to imagine, because technology is fragile. Magnetic storage would be erased at great distances where the field is still strong enough to reorder domains in recording materials. Electrical systems would be disrupted. Conductors would carry induced currents. Components built from metals, semiconductors, and insulating structures would behave unpredictably or fail altogether. Yet even this familiar way of picturing danger is too small to capture the full meaning. The real lesson is that a field capable of disabling simple devices at one distance may reshape atoms and tear matter apart at another. Technology provides a useful ladder of intuition only because it fails earlier than bulk matter does. Devices surrender first, materials surrender later. Atomic structure, under sufficiently extreme conditions, begins to surrender last. There is also an energetic reason the field must be treated as more than an accessory. Magnetic energy density increases with the square of field strength. So when the field becomes enormous, the amount of energy stored in the surrounding space becomes enormous as well. This energy is not inert. It can be transferred into particle acceleration, surface heating, radiation, and mechanical stress on the crust. A twisted magnetic configuration is therefore like a loaded system waiting for rearrangement. When magnetars burst, they are not generating energy from nowhere in the moment. They are releasing energy that has been stored in the magnetic field and in the stressed relation between field and matter. This is why the field is central not only to the appearance of the magnetar, but to its time history. The star evolves by trying to live with an excess of magnetic energy that neither matter nor geometry can contain forever without adjustment. Even the vacuum near the star is not entirely indifferent. In classical intuition, empty space does nothing. It simply permits fields and radiation to pass through it. in quantum electrodynamics. However, the vacuum is not featureless in the deeper sense. It can respond subtly to strong fields through the behavior of virtual particle pairs, giving rise to effects that have no place in ordinary daily experience. Near a magnetar, the field may approach the regime where these quantum vacuum effects become astrophysically relevant. Light moving through the magnetized vacuum can behave as though the vacuum itself has optical properties, with different polarizations propagating differently. This does not mean space becomes a material in the everyday sense, but it does mean that the field is strong enough to push even emptiness away from classical simplicity. Yet the magnetar is not only a magnetic object, it is a compact star whose density and gravity give the field a stage on which to matter maximally. If the same field strength existed without the star's compactness, the consequences would be different. The crust would not be under the same strain. The near-surface region would not be so compressed. What makes the magnetar distinctive is the combination: stellar mass compressed into a city-sized remnant, a rigid crust over an exotic interior, a magnetic field strong enough to dominate particles and challenge matter. These properties reinforce one another. The field gains significance because it is wound into compact matter. The compact matter gains a new form of instability because it must support the field. By the end of this picture, the magnetar field no longer resembles the magnetic phenomena known from planets, machines, or even ordinary stars. It looks instead like a force regime that can climb the hierarchy of matter from device to material to atom, changing behavior at each level and storing enough energy to make the star's outer life one of continual strain. The difficulty is no longer imagining that the field is strong. The difficulty is recognizing that strong is too weak a word. Near a magnetar, magnetism ceases to be a property added to matter. It becomes one of the conditions under which matter is allowed to exist at all, and once a field reaches that level. The next question is no longer what it does to objects placed nearby. The next question is what it does to space itself. Once even the vacuum can no longer remain entirely unchanged in its presence. Empty space is usually treated as the most passive thing in the universe. It separates stars, carries light, and offers fields a place to extend, but it is not expected to answer back. Around a magnetar, that assumption begins to fail. The star's magnetic field is so extreme that it does not merely act on matter near the surface or guide particles through the magnetosphere. It pushes the environment toward a regime where even the vacuum of space may develop measurable optical behavior. This is one of the strangest consequences of magnetar physics, because it moves the mystery beyond the star itself. Density and gravity explain why the remnant is compact. Magnetic stress explains why the crust can crack and flare. But vacuum effects suggest something more subtle and, in a certain way, more unsettling. They suggest that the field is so strong that space near the star can no longer be treated as an empty classical backdrop. Instead, it becomes part of the phenomenon, a region where light may travel differently depending on its polarization, as though the vacuum had acquired a faint internal grain under the pressure of the field. The magnetar does not simply illuminate surrounding emptiness. It conditions that emptiness until the act of passing through it changes. The idea begins in quantum electrodynamics, where the vacuum is not truly nothing in the simplest sense. Even when no real particles are present, the vacuum is described as a restless quantum state in which fleeting virtual particle pairs can influence physical processes. Under ordinary conditions, these effects are subtle, folded into the precise behavior of light and charged particles, and far removed from common experience. But a magnetar is not an ordinary condition. Its field can approach the scale at which those vacuum corrections stop being merely a refinement and become an astrophysical feature. In such a regime, the vacuum can respond to the field in a way that gives it optical anisotropy. meaning light polarized in one direction may propagate differently from light polarized in another. This is often described as vacuum birefringence. The phrase sounds technical, but its meaning is quietly remarkable. It implies that light moving through magnetized empty space may split into modes, each one experiencing the vacuum in a slightly different way, rather as light does when passing through certain crystals. The difference is that there is no crystal there, only the field and the altered quantum behavior of the vacuum itself. That distinction matters because it marks a new threshold in the Magnetar story. Earlier extremes still involve matter in clear forms. The crust fractures. The core contains exotic phases. The magnetic field deforms atoms and channels plasma. Vacuum birefringence goes farther. It suggests that the field is strong enough to modify not just material structures, but the behavior of the most apparently empty regions outside the star. In a calmer part of space, light is expected to cross the vacuum without preference for one polarization over another. Near a magnetar, the field can create a preferred structure in the optical properties of the vacuum, so that the path and polarization of the escaping radiation carry traces of the field's presence even before they encounter gas, dust, or detectors. The star in this sense is not only a source of light, it is a maker of conditions through which that light must travel, and those conditions may be so unusual that the distinction between medium and emptiness begins to blur. This has important consequences for observation. Radiation leaving the surface of a magnetar already faces gravitational redshift, light bending, and the complexities of emission from a hot crust and active magnetosphere. If vacuum birefringence is significant, the polarization state of that light can be altered or stabilized as it travels outward through the strong magnetic field. This means polarimetry. The measurement of light's polarization becomes more than a supporting technique. It becomes one of the rare tools capable of probing the physics of the space around the star itself. A certain pattern of polarization may indicate not only the geometry of the magnetic field, but the influence of quantum vacuum effects on the escaping radiation. This is one reason magnetars and related neutron stars hold such fascination for high-energy astrophysics. They offer a setting where precise observation of a light may test predictions that are otherwise difficult to examine directly. The star becomes a natural experiment, not because it was built for clarity, but because its field is so extreme that it pushes established theory into a rarer observational domain. The optical consequence can be pictured with restraint. Light leaving a magnetar may not simply spread outward as an untroubled wavefront. Instead, different polarization components can be favored or separated in their behavior, producing a more ordered polarization signal than might otherwise survive through the complicated environment above the surface. In effect, the magnetized vacuum can act as a kind of filter, aligning the propagation properties of the radiation with the geometry of the field. This does not necessarily create a dramatic visual display in the ordinary sense, but it changes the deep structure of the emitted light. A detector capable of measuring polarization is then not just recording brightness. It is reading the imprint of a field so intense that the vacuum itself has participated in shaping the signal. That is a level of environmental influence that few other astrophysical objects can offer. There is also a more local consequence near the surface, where the field is strongest and the distinction between atmosphere, magnetosphere, and modified vacuum becomes especially delicate. A magnetar may possess only a thin atmosphere, perhaps composed of light elements or more complex ions under extraordinary conditions. Yet even this tenuous layer interacts with the field in ways that complicate radiative transfer. The vacuum response does not replace those effects. It joins them. Light may be emitted from the hot crust, scattered through a magnetized atmosphere, pass into a magnetosphere full of constrained particles, and all the while propagate through a region where the vacuum itself is not behaving in the simplest classical manner. This creates a layered problem for theory. To interpret a magnetar's observed polarization, spectrum, and pulse profile, one must disentangle surface temperature distribution, magnetic field geometry, atmospheric composition, plasma effects, and vacuum birefringence all at once. The vacuum does not end the mystery. It changes the shape of it by becoming one more active ingredient in the chain between source and observer. What makes this scientifically powerful is that vacuum birefringence is not an invented flourish, added to make magnetars seem more exotic. It arises from a well-developed theoretical framework and becomes relevant here, because the field strength crosses into the necessary regime. Magnetars therefore occupy a rare position in physics. They are distant astronomical remnants, yet they bear on foundational questions about how light and the quantum vacuum behave under extreme conditions. Few laboratories on Earth can come close to such fields, and none can reproduce the full compact star environment in which the effect is expected to matter. The magnetar becomes valuable not only as an endpoint of stellar evolution, but as a bridge between astrophysics and quantum field theory. It is an object whose visible and invisible properties force different areas of physics into the same frame. There is, however, an important caution in how this is understood. The vacuum near a magnetar does not become a material substance in the everyday sense. It does not turn into gas or fluid, and it does not gain texture that could be touched or seen directly with ordinary sight. The change is subtler and more precise. The propagation of light responds to the field through quantum effects, giving the vacuum effective optical properties without making it ordinary matter. This distinction preserves the calm intellectual dignity of the subject. The phenomenon is strange, but it is not fantasy. It is a prediction of known physics under extraordinary circumstances, and magnetars are among the few real places where the needed circumstances appear to exist. Seen from farther out, this means the magnetar alters its surroundings at several nested levels. Gravity bends the geometry of light. The magnetic field governs particles and stores explosive energy. Matter near the surface is distorted into unfamiliar atomic and crustal states. Beyond that, even empty space may become optically responsive to the field. The result is that almost nothing near the star remains entirely untouched by its conditions. Surface, atmosphere, magnetosphere, and vacuum all join the same physical conversation. The magnetar is not extreme in one isolated respect. It is extreme in a cumulative way, each layer of physics pressing into the next until ordinary assumptions about what remains passive have largely run out. By the end of this view, the field has extended its reach beyond matter and into the behavior of the vacuum itself. Yet even this does not settle the deeper problem of the star. It clarifies that magnetars can influence light at astonishing levels of subtlety, but it does not fully answer how often these conditions arise, how internal field geometry evolves, or how the visible activity of the remnant connects to the hidden architecture beneath the crust. The emptiness around the star may no longer be entirely empty in its optical behavior, but the star's own history remains partly concealed. That is the final turn of the magnetar's strangeness. The stronger the field becomes, the more of the environment it recruits into the story, and yet the object at the center still resists full interpretation. Even when space itself begins to react, the remnant keeps some of its meaning in reserve. The deepest difficulty with magnetars is that they are easiest to recognize after the most decisive parts of their story are already over. By the time a magnetar is observed as a pulsing X-ray source, by the time it flares, by the time its crust betrays the stress of an overpowering magnetic field, the object has already passed through collapse, cooling, field amplification, crust formation, and early evolution. Observation begins late. This is why magnetars remain scientifically unfinished in a way that feels appropriate to their nature. They are not hidden because they are too faint in every sense. Often they are conspicuous. They burst. They radiate. They announce themselves in high energy bands with unmistakable force. But the crucial transitions that make them what they are happen deep inside compact matter, during brief early intervals, or beneath layers that no telescope can simply look through. What science receives is the aftermath expressed as surface behavior. The remnant is visible. The making of the remnant is still partly inferred. That difference is what keeps magnetars from settling into a closed category. They are established objects, but not fully resolved ones, and nearly every major feature that defines them still opens outward into a harder question. The first of those questions concerns formation. Not every neutron star becomes a magnetar. Only a minority seem to enter this more extreme magnetic state, and the reason for that branching remains incomplete. Rapid birth rotation offers one route. Strong inherited fields from the progenitor offer another. A combination of both may be required in some cases. Yet each of these pictures contains uncertainties. Birth spin is difficult to reconstruct after the field has already slowed the star. The magnetic structure of the progenitor is not always recoverable from the remnant. The details of the newborn neutron star interior, where convection, differential rotation, neutrino transport, and matter composition interact in a matter of seconds, remain beyond direct observation. The problem is not that science lacks ideas. The problem is that several plausible pathways may overlap, and the decisive evidence that would sort them cleanly is hidden in the most inaccessible phase of the star's life. A Magnetars observed today may preserve the consequences of its birth without preserving a clear record of how that birth unfolded. The field is real. The later violence is real. The exact route from collapse to magnetic dominance is still under negotiation. The second major uncertainty lies inside the star. Magnetars are built from the same compact matter that makes neutron stars valuable to nuclear physics, but their magnetic extremity may alter that matter's behavior in important ways. The crust is thought to be exceptionally strong, yet exactly how strong and how that strength changes with composition, temperature, and field geometry remains an active problem. The inner crust may contain nuclear pasta, but the mechanical and thermal consequences of that phase are still being worked out. The outer core may include superfluid neutrons and superconducting protons, but the coupling between those components and an evolving ultra-strong magnetic field is not fully settled. The inner core may contain more exotic forms of matter, perhaps hyperons or quark phases, but observations have not yet forced one answer. Every layer of the star invites theory inward and then stops it partway. The interior is not merely hard to observe because it is buried. It is hard to observe because the physics itself changes with depth, and each transition introduces a new equation of state, a new transport problem, a new question about how matter stores stress and responds to field evolution. The magnetar is therefore not one mystery but a stack of them, arranged from crust to center. Field geometry deepens this uncertainty still further. The magnetic field inferred from spin behavior may represent only the large-scale exterior component, while much of the truly important structure remains hidden beneath the surface. Internal toroidal fields may be stronger than the dipole field visible from afar. Localized twists in the magnetosphere may come and go. Some magnetars with similar inferred dipole strengths behave differently, suggesting that the number attached to the field is not the whole story. This raises a difficult interpretive problem. If the hidden architecture of the field matters more than the measured exterior value, then the most important part of the magnetar may be the part least directly accessible. A flare may reveal that the field is storing stress, but not exactly where or in what form. A pulse profile may suggest hotspots and magnetic asymmetry, but not uniquely determine the geometry below. Even the distinction between what is happening in the crust and what is happening in the magnetosphere may remain blurred, because the two regions are coupled through the same field. The star behaves as one magnetic system, but observation tends to sample only fragments of that system at a time. There is also the question of lifetime. Magnetars appear rare, and part of that rarity may be genuine, reflecting uncommon birth conditions. But part may also arise from evolution. A magnetar may not remain recognizably magnetar-like forever. Its field can decay, its bursts can become less frequent, its X-ray output can diminish. Over long periods, the star may fade toward less dramatic states, perhaps becoming harder to distinguish from other neutron star populations. This means the magnetar class may be only the visible phase of a longer history. Some quiet neutron stars may be old magnetars whose fiercest era has passed. Some high magnetic field pulsars may occupy neighbouring ground. Not fully separate, but not fully identical. If that is true, then the neutron star family is not divided into neat boxes but into overlapping evolutionary tracks, with magnetars representing one intense interval along a broader continuum. The difficulty is no longer just counting how many magnetars exist. The difficulty is knowing when a neutron star enters the magnetar state, how long it remains there, and what signs persist after the overt activity subsides. Another open problem concerns the relation between magnetars and other transient phenomena in the sky. In recent years, magnetars have been discussed as possible sources for at least some fast radio bursts, those brief and powerful flashes of radio emission that appear from cosmological distances and whose origins are varied and still debated. The connection is compelling because magnetars clearly possess the energy, the magnetic environment, and the eruptive behavior needed for at least certain classes of such bursts. Yet even here the answer is not complete. Some fast radio bursts repeat, some do not. Some are associated with environments suggestive of young energetic remnants. Others arise in older stellar populations. Magnetars may explain part of the phenomenon without explaining all of it. This pattern repeats across the broader study of these stars. Again and again they offer a plausible center for extreme observations, and again the data suggest that the real picture may be more diverse, more conditional, and more dependent on hidden structure than the simplest model first implies. What magnetars reveal about physics may be their most enduring importance. They stand at a junction where stellar evolution, nuclear matter, quantum electrodynamics, plasma physics, and general relativity all become relevant at once. Few objects force so many domains into the same frame. A magnetar is born through stellar collapse, survives through dense matter pressure, cools through neutrino and thermal processes, radiates through surface and magnetospheric emission, cracks under magnetic stress, and may even alter the propagation of light through the vacuum surrounding it. That concentration of physics is rare. It means that magnetars are not only objects to be explained, but tools with which to test explanation itself. Better measurements of mass, radius, polarization, burst timing, and long-term field evolution do not merely refine the portrait of one class of neutron star. They pressure several theories at once, asking whether matter, radiation, and fields behave under these conditions as the models predict. A magnetar is therefore valuable even where it remains uncertain. Its incompleteness is part of its scientific use. There is a calm irony in that. These stars are often described in terms of violence, and the description is justified. They are among the most dangerous environments that a stable stellar remnant can create. Yet their scientific meaning is not only explosive, it is also patient. A magnetar can spend years revealing itself through timing, spectra, cooling, and intermittent outbursts, allowing observers to gather one fragment after another. The object does not surrender its truth in one dramatic event. It has to be watched. Its pulses must be measured. Its flares must be compared. Its quiet intervals matter as much as its violent ones. This slower aspect of magnetar science is easy to overlook, but it is essential. A star built in seconds may require decades of observation to partially understand. The violence of its origin does not remove the need for patience. It makes patience more necessary. By the end of this journey, the magnetar remains what it was from the beginning, a dead star that refuses to behave like a simple ending. It is the remnant of stellar collapse, but also a field source powerful enough to stress matter toward fracture. It is a compact object whose gravity bends light, whose crust may crack like a shell under impossible tension, whose interior may contain phases of matter not seen elsewhere, and whose surrounding space may itself respond to the pressure of its magnetic field. Yet after all of that, the most important fact may be that the object still resists closure. Its formation is not fully settled, its interior is not fully mapped, its field is not fully exposed, its place among other neutron stars is not fully simplified. Everything learned so far can be arranged into a coherent story, but not yet into a finished one, and that unfinished quality is exactly what keeps the magnetar important. It is not merely an extreme object in the universe. It is one of the places where the universe continues to show how much extreme conditions can still keep in reserve. In the end, a magnetar remains difficult not because it hides entirely, but because each thing it reveals opens into a deeper layer that has not yet settled. Its bursts can be measured, its pulses can be tracked, its field can be inferred from the slowing of its spin and the violence of its outbursts. Yet the star itself remains partly withdrawn inside conditions too compressed, too magnetized, and too distant to be known in any simple way. That is part of what gives it such lasting weight in science. A magnetar is not only one more strange object added to an already strange universe. It is a place where several frontiers meet at once, where stellar death gives rise to compact matter, where compact matter gives rise to stresses no ordinary solid could endure, and where magnetism rises to a level that begins to shape not only the star, but the behavior of light and emptiness around it, even after the largest flares have faded, even after the pulses have been timed and the spectra examined. Something remains unfinished at the center of the story. The remnant still asks how matter behaves when pressed so far beyond familiar limits, how fields evolve when they become strong enough to dominate a star's outer life, and how much of the hidden interior can ever be read from the brief signals that escape. In that sense, the magnetar does not stand merely as a violent endpoint. It stands as a quiet reminder that some of the most revealing places in the universe are also the least easily resolved. The collapse that formed it is over. The supernova light is long gone. But the object left behind continues, slowly and intermittently, to release fragments of an answer that is not yet complete, and perhaps will remain open for a very long time,